The idea in this video is to walk you through a rather complex Gras GIS simulation using Python. So here I am in the classical Gras GIS environment. I simply started the simple Python editor that is part of Gras GIS. So you can go here on Python and go on the simple editor, and then this window will open where you can import or open Python scripts that you've prepared, or you can write your own Python scripts within this editor. I open here one script I prepared previously. And now I want to walk you through this script line by line. So first of all, I'm doing a bit of housekeeping in respect of Python. I'm importing whatever I need on system and operating system. And most importantly, I import the Gras script commands, and because I don't want to write it every time, I make it a shortcut as GS. And now I'm doing the same procedure we've done before. I'm using the Gras GIS command line. I'm setting a region. In this specific setting here, I decided that this is a 50 meter wide and 200 meter long domain, which is split in 50 rows in 100 columns. I assume that I have an hydraulic head difference or hydraulic gradient from east to west by 0.4 meters with a total pressure head of 38 meters. Everything else is pretty much as we've done it before. I define directly boundary conditions in left and right. And I'm defining a few raster maps which I need for the groundwater flow module. So I'm introducing a specific raster map just full of zeros, which I call null. And I'm defining the top layer, which is 45 meters. So I have roughly 77 meters between the top of the surface and the depth to the water level. Now I want to introduce a bit of heterogeneity. So I'm using heterogeneous map, which I generate based on the Gras GIS command random surface. This takes a couple of parameters. I've shown this in a different video, which just simply gives me a bit of a heterogeneity. I can show you how this map looks like. We can take a look a bit more on the statistics by plotting the histogram of this and looking at the statistics. So I made this one based on the parameters that it varies between 1 and 100. I have a mean which is not precisely 50 but close to it, and I have some standard deviation. So we see, if we look at the histogram, we can see the distribution here. So I will use this heterogeneity map as a blueprint to introduce heterogeneity in the hydraulic connectivity, in the porosity, and later on in the diffusivity of the domain. All right, so I want to have the hydraulic connectivity to vary around this value by some quantity. So I'm having this mean value and then use this heterogeneity map. So the values between there, which vary between 1 and 100, I subtract the mean so that it varies now between pretty much minus 50 and 50. I divided it by 100, so it varies now between minus 0.5 and 0.5. And then I have here the 0.2 and the 6 to make the standard deviation in an order I would like to have. So when we look at the hydraulic connectivity, it looks like this. And I can also look at the statistics of this plot, and we see that we have a mean value. Well, you know, it's kind of approximative. Of course, it's not exactly 0.0015, but it's 0.0149746, so close enough to what I'm looking at, and I can determine my variation here to make the standard deviation part of this line to match the order of spread which I want in terms of hydraulic connectivity. Right. As I discussed in another video, there are more sophisticated methods to represent heterogeneity in groundwater modeling if you have knowledge about the domain in terms of observation data and so on. But here I'm just interested in generating some heterogeneity to have a more interesting flow field for the subsequent tasks we want to do. And I'm not just applying this for the hydraulic connectivity, but as I said, also for the porosity. So you see this all looks very similar, right? So you can see how that one, and also for the diffusivity, right? You see how these all follow the same procedures. So I'm corresponding, of course, this one here with, for example, different rock types where I assume that this kind of type is has a higher hydraulic conductivity, has a higher porosity, and a higher diffusivity. That doesn't have to be the case, but again, for this synthetic case, we want to model here. This is just a nice procedure and some procedure to integrate some heterogeneity into the model. All right, so these are those two lines to introduce you for hydraulic conductivity and porosity. Then I'm just simply conducting a steady state groundwater flow module. So you see the long time span here to achieve a steady state. As you have done in the past in the other videos, I need a very, very small error value and a respective high number of maximum iterations to achieve a sufficient accuracy for those kind of parameters I chose. And now we're done with the groundwater model flow. Now I want to put a Solute Transport model on top of that. But to model Solute Transport, I need to have the groundwater flow module in the background. Of course, the groundwater flow module r.solute.transport requires some additional information, which are similar to the groundwater flow module provided in raster maps. So I need an initial concentration here. I decided for a simple 5 kilograms per cubic meter initial concentration at one point, so in one cell. We have to define boundary conditions, so we will have no flow boundary conditions on all sides, but the transient boundary conditions on the left, on the right, so that the tracer can escape of our domain in flow direction. As I already said, I'm introducing the diffusivity similarly to hydraulic connectivity and porosity based on the heterogeneity of the domain. And I'm neglecting any kind of transmissivity at this point. On the same time, I want to take daily measurements at some observation points. So the standard operating folder, that's also where I stored this file of Gras GIS, is your home folder. So for simplicity, I decided to store all values on the desktop. So I can simply provide here a relative path. So with the dot, I'm in my home folder, going to the desktop folder, and I previously prepared this text file, which does not do anything else than having the points coordinates. So it's located in the middle, exactly also where I specify the tracer injection, or the solute initial concentration, to put it in a more general way. And then the X column is just simply the column number on the for the observation points. So I have this in 30, 60, 90, pardon, it's not column, it's meters, in 39, 60, and 90 meters distance from the left side, as I'm injecting on the after 5 meters, so then it's respective on the right to this one. So this is what I'm doing here. I'm calling the vector map reading in ASCII file format. This is a path to my file. This is the name of the vector map which I want to use. And I'm saying that within this file, the values are separated by comma, as you can see here. So now I just loaded the vector map. So what I then have to do separately in Gras GIS, if I do it this way, is I have to add an attribute table to this specific raster map. I'm doing this by just simply calling this command, vector map database add table. And now to this table, I'm adding columns. And I'm adding a column for each day to store the value observed at this day at this specific observation points. So this is what I'm doing here. So I'm calling it how to call the column. So it's day 1 to day 30, and it's a double precision column. So it means it's a float value with a double precision. So respective bit number is reserved. Then I'm quickly doing one small time step. You see here, it's just very, very small to have an initial diffusion. Note again here that you need to provide a water source term, which is null due to a bug in the so mistake in the Solute Transport flow module. Physically, this is not necessary, but it needs it because of a mistake. But as you see, I can simply set it to 0, so we don't change the physics. It's just, as I said, a bug in the computer code. Otherwise, if you do not provide the water source, it will run into a problem. So we do this simply to have an initial distribution, and then we can now subsequently calculate the following 30 days. So what we do here is now we're using a for loop. So there's a different kind of loops. You might know already while loops. So here we're using a for loop, and it can simply be read as a grammar sentences. So for the variable t, which is in the range between 0 and 30 with a step size of 1. So that means it will compute the 2 following commands, because then I'm beginning on the left side again. It will compute the following 2 commands for 0, for 1, for 2, for 3, for 5, and so on, for 29, for 30, and then it will stop. And for each of those time steps, I'm running the command r.solute.transport, and with the specified parameters. So I'm specifying the solver, which I do not really need to do because it's the standard setting. I'm providing it with all the raster maps that are required. And again, I'm using this trick that I provide the output as my current time step plus 1, so that I can use the initial setting based on the time step of the previous time step, so of the result which I've done in the loop step before. Right, so that's why I did this initial time step here. I generated my 0 value pretty much. Okay, and now I can use this 0 value here and to calculate the time step after 1 day. This is what I do, and then in the same loop I'm running the command what_rest, which simply extracts the values from the raster map for the coordinates of the vector points, right? And the vector point map which I'm using here is of course the ones I just generated above for the observation points, and the values from each raster map, so from the concentration map we just computed, I write to the respective column of the attribute table for each vector point which we just generated. Again, this we do for the 30 subsequent days, and then I'm just doing one very simple thing at the end. I'm exporting my attribute table of those observation point vector map to a file. I'm storing that one again on the desktop so that I can subsequently analyze those kind of observation points using Excel and so on. I did another video for this topic. All right, so I just simply do this at the end. Now we can look, for example, here how the final a tracer concentration looks like. So we started with a point source somewhere over here, and now you can see a bit the effect of the heterogeneity, how that influenced the heterogeneous tracer concentration in the end, right? So if this all would have been homogeneous, this would have been a very straightforward, very symmetric geometric body, but due to the heterogeneity you see that there is some variations in the tracer concentration. So you might note this is quite a complex simulation here, but now we're already advanced in using Gras GIS or Gras GIS for groundwater modeling and solute transport. So I think this is a nice way to wrap it up, to get you used a bit to Python, not very much, but now you also learned what a for loop is doing. And you can see how you can, of course, generate very, very powerful simulations with, well, not so much actually, it's just like a bit less than 120 lines of code with a lot of documentation from my side. So this is a really nice example to demonstrate just simply the power of Gras GIS for the groundwater modeling tool. Of course, you could vary a lot of things here, making things more complex, introducing other changes. But this is what I wanted to do here. One last comment regarding stability. So you might know that the Solute Transport module, similar to the groundwater flow module, is based on an implicit solver. However, it allows you to, if you use the graphical user interface, it allows you to set a flag so that it computes the maximum time step that would be allowed by the current Friedrich-Levy stability criteria and applies automatically this time step to the simulation, not because of stability concerns, but because of accuracy concerns. The problem is you don't have this applicability using the automatic time step control based on the CFL criteria if you use Python in the command line. So you have to use a little bit of workaround, because you can define the number of loops. What simply does is it takes a time step and divides it by the number of loops, which means if I have 86,400 seconds, which is a day what I want to simulate, and I define on the other hand a number of loops equals 10, it will actually compute 10 times a simulation with a time step of 8,640. The number loops of 10 is quite high. It's not required for a CFL, so 2 would be sufficient. But I just put in 10 there for no specific reason. You can increase the number even further. It doesn't change much besides increasing your computational costs. But with 10, it was still very, very quick and very performant on my PC. But the least number you should put here, you're required to put here, is a number 2 to fulfill the CFL criteria. If you do not specify it, it will do a time step. It will do the full time step in one calculation, which might lead to inaccuracy. But I strongly encourage you to try it out, to play around with those kind of parameters to see what the effect is. In fact, I will do another video demonstrating just the effects of, for example, modifying the time step, but also modifying other things of this simulation. I hope you understood how this script is designed and how you can use a Python script, or more general, how you can use Gras GIS to conduct more complex simulations. And I also hope you understood a bit how the concept is behind designing more complex simulations. It always is the same: defining geometry, setting up the parameters, calculating background information, calculating, for example, the steady state groundwater flow, or having some other basic calculations beforehand which are static, which do not change over time. Preparing the design to store data, right? Think about visualization and what kind of data you want to save early on. I did told this to you a couple times in the past. All right, and then how to actually conduct the simulation in a time evolving manner with the spatial resolution you want to achieve here. So thank you very much for your attention, and have fun to play around with the Gras GIS groundwater and solute transport module, and try to start to modify parameters and see what the effect is.